Okay. I need to get this on the video that the whole class smells like garlic.
It's not you.
Why do I smell so much like garlic? All right, this is serious. So we are undoubtedly, not just undoubtedly, undoubtedly in the, oh, I just smelled the garlic. In the middle of the two most interesting, coolest topics in this class. So the two coolest topics in this class number one is linkages. And number two is particle kinematics and kinetics. In a rotating coordinate system. Okay, so we're on linkages right now. I'm going to do one more example of a linkage problem. And then we're going on to this one, which is a real like mind bender. So yeah, we'll all talk a lot more about that when we get to it. We might get to the start of it today, but this is just to say this is a great time to be alive. This next couple of classes. Okay, so linkages. Let's do another example. So let's say that we have a pin joint connected to the ground, and then two members at angles of 45 degrees connected by a pin. It's not a very good pin. Let's say that each one has a length of 0.5. I'll call this one member 1, the bottom one, and then this one's member 2, and I'll call the joints A, B, and C up at the top. And let's say that at the instant shown, angular velocity of member 1 is, well, the same as the angular velocity of member 2, and that's positive 10 radians per second. Okay, so how many seconds does it take for a revolution? Well, 10 radians, one revolution is about 6 radians. You know, 6, like 2 pi radians. So that's, I don't know, I think just center yourself on stuff like that when you see it. So it's about 1.5 seconds or something, you know. 2 pi. So 6.2. What? That would be if it was 1 radian per second. No, 10 radians per second. So it's going 1. Oh yeah, I did the inverse. Yeah, right. So it's going like 1.5 revolutions every second, something like that. And let's say that there is at this instant an external couple of plus 100. That's a lot. Let's do less than that. Say 20 plus 20 Newton meters on member 1 and minus 20 Newton meters on member 2. And we want to calculate the acceleration at that point C. The masses of these two things are each 5 kilograms. Okay, and that's it. So, first of all, I said this was angular velocity of positive 10, but that should be negative 10, the way I think of it. Yes? Well, the couple is either acting on one body or the other. You know, if you think of it as two forces, so it has to be two separate things. But this is sort of an interesting. So this is supposed to be kind of the most basic model you can think of like a person's leg. You know, so this is sort of like a first look at like a biomechanics type calculation. Okay, so this person's shank, lower leg is well. So let's think about those rotations. What does that mean if both of these two have angular velocities of negative 10 radians per second? What's happening here? Negative 10. So this one's rotating this way, right, clockwise. What's this one doing? Is that angle changing, staying the same? Like that knee angle. It's staying the same. That's exactly right. These two things are both rotating with the same angular velocity, and so the angle between them isn't changing, and the whole thing is just rotating like this. Like this person has a bent knee, and they're just tipping down towards the ground. Okay. And those external couples, it's sort of an interesting fact that what a muscle does, this isn't an interesting fact, you probably figured this out in your time on this earth, but what a muscle does is apply a force to one joint up there and an equal and opposite force to the other joint. It's just like a cable pulling between the two things. But you can always represent that, and it makes the math easier, as a couple and an equal and opposite couple on the two adjacent members. So you can think of this as like a quadricep force or something is causing this couple. So the person's tipping like this, and they're firing their thigh muscles to straighten out their leg. So what happens if you're tipping like this and you abruptly straighten out your leg as that's happening? Well, we would guess there's going to be some kind of like upward acceleration there. Yes, you can think of that. Yeah. Yeah, well, you can exactly, so think of, like if you think of, what that couple is if you think of there being like a muscle force between those two, it's producing a force this way from the muscle and a reaction force counteracting that at the knee. So that's one couple, and then the equal and opposite one on the other one. So yeah, you can think of it as a muscle pulling those two things together, and then equal and opposite contact forces at the knee. That's what the couple's coming from. All right, so let's do this calculation. So what's the first step with linkages? So this is like layers and layers of steps, but okay. So what we want to do is isolate one at a time, isolate each one of the rigid bodies, go through those 6 or 7, I guess the 6 steps that you do for rigid bodies for each one. Okay, we're going to come up with a set of equations from Newton's laws for each member. And at that point, we're going to sort of count them up, count up our variables, see where we stand, see how many constraints we need. Okay, so the first step is isolate each body and go through the rigid body steps. So first, member 1. Does member 1 have a fixed point? Your foot is in contact with the floor, so basically your foot is connected to the floor, and number 1 is supposed to be your lower leg. So this pin joint at A is supposed to be like the ankle. It's fixed at A, and that means that the about point is A. The next thing we want to do is calculate the moment of inertia about A, about that fixed point. The moment of inertia about A is equal to the moment of inertia about the center of mass plus md squared. What's the moment of inertia for this? Yep, 1/12 times the mass times the length squared. And we don't have a width, so that means we're just assuming that it's small enough that we can neglect it. So 0.5 squared. And then plus the mass times the distance from the center of mass to the fixed point, to the about point. What's that distance? That's right. The whole thing is 0.5, so from the center of mass to one end, it's 0.5. And I think that is 0.41, and then 6 is repeating. Any questions about that? And then third step is a free body diagram. Okay, so what loads are acting? There's a weight, 5 times 9.81, so 49.05 down. The lower left end is connected to a pin joint, so that's an unknown force vector. I'll call that RA. Then there's a pin joint connecting this to member 2 at the upper right corner, and so that's an unknown force vector that I'll call the force on 1 by 2. And then the last thing is that external couple that I said was applied. On member 1, that's a positive 100 Newton meter couple. So that's this way with a value of, what did I change it to, 20? Any questions about the free body diagram? So now we can write out row vectors, force vectors, moment vectors. We need to choose an about point. No, we don't in this class. Sorry, I was thinking of statics. In this class, we've already chosen the about point. It has to be at A. So here's the about point. So the row vector for that force RA is 0. The force vector is RA, X and Y components. And there's no moment. Yeah, it's 45 degrees. And then what's the row vector for the weight force? Yeah. So that's like 0.17 time. So it's 0.25 times cosine and sine of 45. And I think that is 0.1767. 0.1767. Force vector is 49.05 in the negative y direction. And that cross product is negative 8.667. Then we have the force F12. That's 0.5 times cosine and sine of 45. So that's 535. Force vector is F12x, F12y. And so the cross product is 0.3535 F12y minus 0.3535 F12x. And then the last thing we have to account for is the couple. So that's just, it's counterclockwise, so that's positive 20. And now we'll go to, oh, that was 4. So now step 5 is Newton's second law. Do we need it? Right, there's a fixed point, so no Newton's second law. So step 6 is the rotational equation. So we're going to add up all these moments and set them equal to the moment of inertia times alpha. So negative 8.667. I'm just reordering these. Minus 0.3535 F12x plus 0.3535 F12y plus 20 is equal to 0.416 repeating times alpha 1. And so our first useful equation says negative 0.3535 F12x plus 0.3535 F12y minus 0.416 repeating alpha 1 is equal to negative 11.3 repeating positive, negative 11.3 repeating. Going back and forth between repeating symbols and significant figures and stuff is a really good idea. I don't know. Maybe other people have told you it's not, but it is. No. You just need to know how to do it because when you go to other classes, people are going to care. But I don't care about that because if my results aren't accurate enough, I go back to the top of my program and change all my floating point decimals to double precision floating point decimals, and that fixes it. So, some practical advice for you. I hope not. Okay, so that's the first body. We have one useful equation. And now we go to number 2. So step 1, does member 2 have a fixed point? Nope. So the about point is the center of mass. And so the moment of inertia about the center of mass is 1/12 times the mass times the length squared. We don't need parallel axis theorem. And that gives 0.104. And then 3, free body diagram. Okay, so what do we have? We have the weight. 5 times 9.81 is 49.05. We have a contact force at the connection between the two bodies. That's the force on 2 by 1. We already have F12, so I'm going to call this negative F12 by Newton's third law. And the last thing we have is the couple. This is a couple of negative 100 Newton meters. So this is a clockwise couple with a magnitude 20. I changed it to 20. Clockwise couple of 20 Newton meters. Any questions about the free body diagram? So now rho, force, moment. Our about point this time is the center of mass. So for the weight force, the about point is the rho vector is 0. The force is 0, negative 49.05. No moment. And then for negative F12, rho vector is 0.25 times cosine and sine of negative 45. That's 0.1767, negative 0.1767. The force vector is negative F12x, negative F12y. And so the moment is negative 0.1767 F12y minus 0.1767 F12x. And then we just have the couple left, and that's negative 20. Step 5, do we need Newton's second law for this one? Yep. So 0, negative 49.05 plus negative F12x, negative F12y is equal to the mass times the acceleration of the center of mass. I'll just call that A2x, A2y, but we have to remember that represents the center of mass of that body. That gives us equation double star, which says negative F12x minus 5 A2x is equal to 0. And equation triple star says negative F12y minus 5A2y is equal to positive 49.05. And then step 6 is the rotational equation. So that says negative 0.1767 F12x minus 0.1767 F12y minus 20 is equal to 0.104 times alpha 2, and that gives us equation quadruple star that says negative 0.1767 F12x minus 0.1767 F12y minus 0.104 alpha 2 is equal to 20. So now, after Newton's laws, we have 4 equations, and the variables we have are the vector f12 and alpha 1. And then the vector a2 and then the vector the scalar alpha 2. This time we have 1, 2, 3, 4, 5, 6 variables. In the last example we did, remember we had a triangular shaped thing that had a pin joint connecting the two members, and then it had a pin and slot joint at one end, and I guess it was facing this way. Right? And the pin in the slot could slide up and down. Do you remember how many variables we had in that example? 7. We had 7. This time we have 6. What's going on there? What's the difference? Let's look back at the shape itself. Yeah, that's right. So there, you can only come up with these constraint equations at joints that aren't fixed. In the example before, we had a joint where we could find constraints at the equivalent of b, but we also had one at the end that would give us one variable. This time we only have one joint that's relevant for the constraints. So all we can do is constrain the acceleration at b. That's two equations, an x and a y equation setting those accelerations equal. And so the number of constraints that you need is going to always work out with the number of equations you can come up with for those joints. It's cool how that works. I mean, it has to be that way or you couldn't solve it. Okay, so we need 2 constraint equations. And those 2 constraint equations are going to come from saying that the members' accelerations must match at b. So we're going to calculate the acceleration of b according to member 1, calculate the acceleration of b according to member 2, and then set those 2 equal. So first, the acceleration of b according to number 1. So if you think about what b is doing according to member 1, It's just moving in a circular path around A. It's supposed to be a circle. Okay. So we can just use circular motion with this as the center of the circle. So the acceleration of B is equal to alpha 1 cross R, and that R is going to go from, so where is that R vector going to go? From A to B. So I don't know, I'm going to write this as like 2B from A, sort of like the force notation I use, plus omega cross quantity, omega cross R BA. It's A to B, but you know, like I'm going to write it this way because I do the forces as the force on 1 by 2, so I'm going to do this as the. So what the vector we want is the point B minus the point A. All right, so let's write out what all these are. Alpha 1 is 0, 0, scalar alpha 1. Omega 1 is, remember 1, omega was, for both of them it was negative 10. This is 0, 0, negative 10. And then what's our vector 2B from A? That's right. So that's 0.3535, 0.3535. And so the acceleration of B, according to member 1, is 0, 0, alpha 1, crossed with 0.3535, 0.3535, 0, plus 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross 0.3535, 0.3535, 0. And that gives negative 0.3535 alpha 1 minus 35.35. And then for the y component, positive 0.3535 alpha 1 minus 35.35. And now the acceleration of B according to member 2. Okay, so there's no fixed point on member 2, so there's no true circular motion of this point B according to member 2. But what we can do is say the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass, and that's a circular motion, plus the acceleration of the center of mass, which is already a variable of ours. And that's the way we're always going to treat those constraints for the member that doesn't have a fixed point, or any member that doesn't have a fixed point. So the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. This one is already our variable A2. And this one is circular motion. So I'll rewrite this. The acceleration of B is equal to alpha 2 crossed with the r vector. Okay, what r vector do we want for this? We're calculating this circular motion we're using is from the center of mass of, like the center of the circle is the center of mass of 2. So the r vector we want is from the center of mass to B. So r goes 2b from the center of mass of 2. That's kind of ugly. And then plus omega 2 crossed with the quantity omega 2 cross r 2b from the center of mass of 2. And then add on a2. Alpha 2 is equal to 0, 0, scalar alpha 2. Question? Omega 2 is given negative 10, and that's in Z, 0, 0, negative 10. And then that R, 2B, from the center of mass of 2, I think that's positive 0.1767, negative 0.17670. So AB is equal to 0, 0, alpha 2 crossed with 0.1767, negative 0.17670, plus 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross 0.1767, negative 0.17670, and then plus A2x, A2y. And so for this one, you get that AB is equal to 0.1767 alpha 2 minus 17.67 plus A2x, and the y component is 0.1767 alpha 2 plus 17.67 plus A2y. And now we're just saying this version of AB is equal to the version of AB from member 1. So our equation 5 star says negative 0.3535 alpha 1 minus A2x minus 0.1767 alpha 2 is equal to 17.67. And 6 star says positive 0.3535 alpha 1 minus A2Y minus 0.1767 alpha 2 is equal to negative 17.67. Now we have 6 equations for 6 variables, and we can solve it. Well, you set them equal, and then I moved everything over to the other side. Let's see. Yeah, that does seem like it would be. Okay, so the constants are both negatives there. The constants are, one's negative there and one's positive, so it seems like they should add in the second one, right? Well, let me just make sure. Don't erase anything yet. So from the first one, we have negative 0.3535 alpha 1 minus. Okay, so negative 0.3535 alpha 1 minus 35.35 is equal to 0.1767 alpha 2 minus 17.67 plus A2x. And the second equation says positive 0.3535 minus. So 0.3535 alpha 1 minus, right? Minus 35.35 is equal to positive 1767 alpha 2 plus 17.67 plus A2y. So equation 5 star should say negative 0.3535 alpha 1 minus 0.1767 alpha 2 minus A2x is equal to positive 17.67. And equation 6 star says positive 0.3535 alpha 1 minus 0.1767 alpha 2 minus A2y is equal to, and yeah, that one should add. So 53.02. Okay, 6 and 6. So now we have to solve this because I changed that couple. Maybe that was, should have just left it in retrospect, but what are we going to do now?
The equations are always going to be acceleration.
Yes.
Acceleration out of joint.
And the reason they're always going to be acceleration is because, you know, you could also come up with restrictions on positions and restrictions on velocities, but we don't care about that. What we want in constraint equations is equations that relate variables we already have from Newton's laws. And that just happens to be accelerations. Okay, so the rows are equations 1, 2, 3, 4, 5, 6. And variables, let's go f12x, f12y, and then a2x, a2y, and then alpha 1 and alpha 2, and then the constant. So equation 1, f12x, we have negative 0.3535. Tell me if you notice a mistake anywhere. F12y is positive 0.3535. Alpha 1 is negative 0.4167. 416 repeating. And then the constant from equation 1 is negative 11.3. Equation 2 says f12x, we have negative 1. a2x, we have negative 5. Everything else is 0. Equation 3, f12y, we have negative 1. a2y, we have negative 5. And the constant is positive 49.05. Equation 4, we have f12x, negative 0.1767. f12y, negative 0.1767. Alpha 2, negative 0.104. And the constant is positive 20. And then equation 5, alpha 1, well, a2x, we have negative 1. Alpha 1, we have negative 0.3535. Alpha 2, we have negative 0.1767. And the constant is positive 17.67. And then equation 6, a2y, we have negative 1. Alpha 2, we have negative 0.1767. Alpha 1, we have 0.3535. And the constant is 53.02. Okay, well, let's finish this one on Wednesday. Any questions so far? We're trying to calculate the acceleration of that top point, that point C. That's right.